So it's time to talk about radicals. Radicals are reactions of alkanes. Alkanes do not do any reaction besides radical stuff. The only kind of intermediate that an alkane will go through is a radical thing. Radicals involve alkanes plus a halogen. Here's one, an alkane plus a halogen. This reaction can be initiated by light, which is this little H nu symbol. Remember, E equals H nu, back from light, electromagnetic radiation stuff. H nu, or heat. That's our little delta symbol. The radical reaction can be initiated by either of those. So we have an alkane plus a halogen. It could be chlorine or bromine, more to be said later. Light or heat, and you replace one of the hydrogens with a halogen. Replace one of the hydrogens on the alkane with a halogen. Back in chapter 5, there was a section on bond enthalpies and the thermodynamics of breaking bonds and making bonds and stuff like that. Back in general chemistry, we did a ton of delta H calculations, looked up values in the back of the textbook, products minus reactants equals delta H for the reaction. Well, in organic, it's a little bit different. Those tables of data in the back of the book, in your Gen Chem book, those were inorganic species. Organic stuff, we usually use bond enthalpies because it's a little bit difficult to list tables and tables and tables of data for organic species because there are just so many of them. It would be a large volume book, and it wouldn't even come close to listing all of the organic molecules that exist. So we use bond enthalpies to calculate delta H for a reaction in organic instead of actual molecule enthalpies. What we do is bonds broken minus bonds made, not products minus reactants, broken minus made. In this reaction, we're breaking a CH bond from methane, that costs that much kilocalories per mole. We're going to break a Cl-Cl bond in order to do this reaction. It costs that much kilocalories per mole. Breaking bonds always requires energy. Making bonds always releases energy. We're making a Cl-C bond in methane. We're making an HCl bond in hydrochloric acid over there. There are our two values there. So if it's broken minus made, there's our whole math. Broken minus made, we actually get a sum of negative 23.8 kilocalories per mole. This is an exothermic reaction. Replacing a hydrogen with a halogen, exothermic reaction. Okay. So these alkanes that undergo radical reactions, they undergo what's called the chain radical reaction. Are you ready to draw a mechanism? Let's try it. The chain radical mechanism is different from all the other reaction types that we have talked about. Oh, I'm bad at writing and spelling. Initiation. What's an A? Initiation. There are three main steps in a chain radical mechanism, and they are listed by name. Initiation, propagation, yep, got that one right, and termination. Initiation, propagation, termination. All right. Initiation, it can be initiated by heat or light, but the way the reaction starts is your chlorine molecule or your bromine molecule spontaneously splits. Yeah, spontaneously splits like this. First thing we need to note. This kind of curved arrow shows movement of 2 electrons. This kind of curved arrow shows movement of 1 electron. If you didn't think so already, I done told you organic chemists are crazy. If there's one little barb on the arrow, that's 1 electron moving. If there are 2 barbs on the arrow, a normal arrow, that's 2 electrons moving. So these are 1 electron moving, and it's splitting into those 2 molecules, a Cl with an extra unpaired electron now, and another Cl with an extra unpaired electron, 2 of the same molecule, actually. That unpaired electron is called a radical. So when I kept saying this goes through a radical mechanism, radical, intermediate, a radical is an unpaired electron. So that's a radical, and that's a radical. We started out with no radicals in this reaction, and we created 2 radicals. An initiation step, no radicals, end with 2 radicals. Yeah? A radical mechanism should always show at least 2 propagation steps based on what we're learning. We're going to start with the radical that we created in the initiation step, and if we draw the mechanism of methane radical, we'll bring in the methane here. A propagation step reacts a radical and a non-radical, like so, to create a radical and a non-radical. Takes a lot of time to put all those extra little dots on there. So this says Cl and H are each sharing 1 electron to make a bond between Cl and H. The extra electron that's left over becomes a radical dot on this carbon. Propagation, radical plus non yields radical plus non. All right, another propagation. Let's start with the radical that we just finished off with. Yeah. And we will add in our initiator up there again, our chlorine radical. Do you have to put in all these lone pair electrons? No, but I'm just trying to keep track of them a little bit because we've got loose free floating radicals around in this mechanism. So I end up making a bond between carbon and chlorine, and radicals meet in the middle of the air like that. It's silly, I know. It's so different from what we've been doing. And I end up with a Cl dot. A chlorine radical got regenerated in this propagation step, and we ended up with a chlorine getting connected to our methyl radical, like that. That little Christmas party down there. So a propagation should always have at least 2 propagation steps. There are my 2 propagation steps. I have a radical and a non reacting to create a radical and a non. A radical and a non reacting to create a radical and a non. Why is this called a chain radical mechanism? Well, those propagation steps are happening all together, all in the same flask, happening again and again and again and again, until some termination happens. But even if one of the radical chains, I got quotes in the air over here, even if one of the radical chains terminates, it could still be initiated or turn into a radical again. So radical reactions are a little bit messy, a little bit unpredictable, kind of based on what we know. We will talk about their predictability in a minute. Hold on. But these things are all happening simultaneously within a flask. You got radicals all over the place. If at any time 2 of those radicals bump into each other, that's where we get termination. Anytime 2 radicals bump into each other, that can cause, or that is the cause of termination. 2 Cl radicals could terminate each other. A Cl radical and a methyl radical. We're going to make this an H3 because I don't have space. A Cl radical and a methyl radical could terminate, like so. 2 methyl radicals could terminate, like this one. And all of a sudden, we've got an ethane in our flask. Once you have a little bit of ethane, that ethane could undergo a radical reaction, and then you could end up with some ethyl substituted chlorine. No, some chloroethane. You could have that ethane turn into a radical and be terminated by another methyl to get you some propane. That propane can undergo some radical stuff. Yeah, you could get a lot of products out of these radical reactions. So the way we draw a chain radical mechanism is different from the way we've been drawing mechanisms for the last few weeks. But the chain radical needs to be presented very stepwise like this. It's not one thing flows into another. It's just different. I'm sorry. All right. So that was what if we chlorinated methane. We get chloromethane. What if you try to chlorinate something that has multiple carbons? Oh, I meant to say this. I forgot. This step, let me see. This step, we'll highlight it, that step is called hydrogen abstraction. So hydrogen abstraction is removing a hydrogen with one electron. It's not a hydride. Hydride is 2 electrons. It's not a proton because protons have no electrons. It's a hydrogen abstraction. So that hydrogen abstraction is a very important step in making radical products, a very important step in an alkane becoming an alkyl halide. Okay. So here is propane. Propane has multiple types of hydrogens. Multiple types of hydrogens could be abstracted. There are primary hydrogens out here on this primary carbons. How many of them? 6. There are secondary hydrogens up there on that secondary carbon. How many of them? 2. So there are 6 primary hydrogens and 2 secondary hydrogens. We could imagine a primary hydrogen being abstracted to make that product. We could imagine a secondary hydrogen being abstracted to create that product. 2 monochlorinated products are possible. 1 chloropropane, 2 chloropropane. All right. Based on the numbers here, we would maybe expect a 3-to-1 ratio of products. We would expect maybe that this one is our major product. However, in real life, that's not the case. In real life, we get 44% this and 56% that. So apparently something else is going on. There's some sort of stabilizing factor. It's not all about statistics. If it were all about statistics, we'd see 3-to-1. It's apparently not all about statistics because we actually have more of the thing we predicted we would have less of. It's about stability of the hydrogens, reactivity of the different types of hydrogens. If a primary hydrogen has a rate of 1, a secondary hydrogen is almost 4 times faster, and a primary hydrogen, that's tertiary. A tertiary hydrogen is almost 5 times faster than a primary. So it's faster to abstract a secondary hydrogen than a primary, and it's even faster to abstract a tertiary hydrogen than a secondary. So that's why we get more of this guy. It's not just all about rates, it's also about thermodynamics and stability. If you try to remove a primary hydrogen, it takes this much energy. If you try to remove, this is a secondary hydrogen, it takes this much energy. That's accounting for the stability of the different radicals that you're creating. So this is creating a primary radical after you abstract that hydrogen. This one is creating a secondary radical after you abstract that hydrogen. A secondary radical is apparently more stable than a primary radical. I can draw conclusions about stabilities of other radicals based on that, like so. I'm saying a benzylic radical is the most stable kind of radical. Then comes allylic, then comes tertiary, secondary, primary, methyl, like so. Have you ever seen a list ordered in this exact same direction, in this exact same order? Yeah. Carbocations follow the exact same trend. Radicals and carbocations are different, but very, very similar in how they behave, in their stability and in their stereochemistry. All right, let's work on some examples stuff. Give the structures of all monochlorinated products formed from the reaction of 2,2,3-trimethylpentane with molecular chlorine, then draw the reaction of each with Katbu. Oh boy. 2,2,3-trimethylpentane. 2,2,3-trimethylpentane with molecular chlorine. We're going to say light. It doesn't say light or heat. Well, what do we get? How many products do we make? Well, I love that this comes toward the end of the first semester so that we can throw it back to, if we were looking at this compound and saying, how many peaks would you expect to see in a proton NMR? How many peaks would you expect to see in a proton NMR? How many peaks would you expect to see in a proton NMR of this guy? Why is that relevant? Why do we go there? Because In order to do a radical reaction, you must have a hydrogen to abstract. So in a proton NMR, only hydrogens show up. So if I gave that guy the letter A, I could give these other methyls also a letter A because they're all chemically equivalent. Replacing a hydrogen here with chlorine is exactly the same product as replacing a hydrogen here or replacing a hydrogen there. Does this carbon need a B? No, there are no hydrogens on that carbon. So I'm going to put no B there. What about a B here? Any other hydrogens like that hydrogen? No. Here's the rest of my letters. You would have known that there are five chemically equivalent types of H's. Yep. What that will mean is we make 5 different constitutional isomers when we react with molecular chlorine. Pause it and draw those 5 constitutional isomers. Go, go, go. Pause it. Go, go, go. You got them all? Yep. These are my 5 constitutional isomers. It says, then draw the reaction of each with Katbu. Okay. To this first one, I add Katbu. It's a primary alkyl halide, which typically means SN2. But Katbu can't really do SN2. Katbu's too bulky for that. Uh-oh, we have another problem. There's no beta hydrogen. So I'm going to say no reaction here because Katbu's too bulky for substitution, and I don't have a beta hydrogen to do elimination. Uh-oh. If I add Katbu to this guy, it's a tertiary alkyl halide. Okay. Anions, yes. Strong base, yes. So then I go through and say beta, 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 beta. Katbu is big and bulky, which means anti self-elimination, whoosh, 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 like that. Ding, ding. Product. All right. Katbu. It's a primary alkyl halide. SN2 is what my flowchart says, but it says E2 is strong base. All right, let's do E2 because Katbu's a strong base. It's pretty crowded to pluck that beta hydrogen, but maybe Katbu could do it. So we get that guy. Oh, look, it's the same as the one right next door. Katbu. It's a secondary alkyl halide. Anions? Yes. Strong base? Yes. Do I take from left beta or right beta? You've been practicing, haven't you? Haven't you? Haven't you? Put that hydrogen, dump in electrons, kick out that thing. We're doing an E2 elimination to give me that. And Katbu up here. It's a primary alkyl halide. SN2. Katbu can't really do SN2. He's too big and bulky for that. So he can take that beta hydrogen. It's a little bit crowded. It's not his favorite place to go. But Katbu can technically take that thing. Woo woo! So out of this elimination, out of these eliminations, we get 2 alkenes and only 2 alkenes. We had 5 different alkyl halides, but we eliminated and only made 2 alkenes. We would have some leftover alkyl halide that didn't get eliminated because that guy is not eliminatable. That guy on the right, on the left, that's the left, the very first one. He's not eliminatable because he doesn't have a hydrogen. All right. So what's cool about this radical stuff is it tells you how to make an alkyl halide, and we just wrapped up all the reactions that alkyl halides do. Isn't it grand? So radicals are very much like carbocations. Radicals are trigonal planar, just like carbocations. So what do you expect the stereochemistry of a radical product to be? I expect it to be the same kind of stereochemistry that a carbocation would give me. So this previous example, we didn't talk about stereochemistry, although we do have some asymmetric carbons in lots of these. We ignored stereochemistry in this one. Let's not ignore stereochemistry in this one. Okay. When R, 2-chlorobutane. Okay. Here's a butane. Here's a chloro. In order to be R, when R, 2-chlorobutane, it's got to be a wedge. When R, 2-chlorobutane, undergoes a reaction with diatomic chlorine in the presence of UV light, UV light, we get some stuff. Give the structures of all compounds produced which have 2 chlorines on them, meaning add 1 more chlorine to the thing that we've got. That's what that says. Give the relationship, how many fractions, oh boy, yep, several questions to answer. But I step backwards and say, in proton NMR, how many signals would you see in the proton NMR of R, 2-chlorobutane? I would expect to see 4 signals, which should mean I have 4 products, 4 constitutional isomers, 4 constitutional isomers of my dichlorinated compounds. All right, let's get on it. 4 compounds. If I keep my chlorine, add chlorine. Keep my chlorine, add another chlorine. Keep my chlorine, add a chlorine. Keep my chlorine, add a chlorine. There are my 4 constitutional isomers, but I said we can't ignore stereochemistry this time. So if we go back and analyze what we've got and talk about stereochemistry of what we've got, this carbon was defined as a wedge in the beginning, and if I'm abstracting a hydrogen from over there and putting in the chlorine, this carbon should not be affected, so that should stay as a wedged chlorine. The chlorine on carbon A is not an asymmetric carbon, so leave it alone. In my next molecule, I have 2 chlorines on this thing now. That's not an asymmetric center anymore. No dashes or wedges needed. In my next molecule, carbon B had nothing happen to it, so that should stay as a wedge. And when carbon C, when that hydrogen gets abstracted, the chlorine could be added and coming out towards you, or the chlorine could be added and going back away. So I get 2 different products, really, when I abstract a hydrogen from carbon C. When I abstract a hydrogen from carbon D does not make a new asymmetric carbon over here. My carbon B, though, in this last molecule should stay the same. It should stay wedged. Okay, so the next thing says, give the structure of all compounds which have the molecular formula. It doesn't actually say, but we're going to give these guys numbers. 1, 2, 3, 4, 5, so that we can answer the rest of the questions. Give the relationship between all stereoisomers. Number 1 question, which things are stereoisomers? Only 3 and 4 are stereoisomers, and 3 and 4 are diastereomers. Diastereomers. If separated by distillation, how many fractions would be obtained? Well, we've not talked much about distillation, but things that have different boiling points will come out as a different fraction in distillation. What kinds of things should have the same boiling point? Enantiomers. Enantiomers have the exact same physical properties, including boiling point. So enantiomers would distill in a fraction together. Other than that, all compounds should have different boiling points. So I don't have any pairs of enantiomers, so I should actually get 5 fractions in this thing, because 5 different compounds exist. Which of these fractions, if any, would be optically active? So, which would be optically active and optically inactive? So things that are optically active are things that have asymmetric carbons and the enantiomer is not present. Does that make sense? Things that are optically inactive, that's easier to define probably. Things that are optically inactive are anything that has no asymmetric carbon, so it's achiral because it has no asymmetric carbon, or things that are a fraction that would contain both pairs of enantiomers, both enantiomers, or things that are meso. So 3 things can make something optically inactive. No asymmetric carbon, therefore achiral. A pair of enantiomers in the fraction together, therefore racemic, would cancel each other out. Or a meso compound, right hand, left hand, within the same molecule, optically inactive. Okay, you should try to assign these, but I'm going to do it for you, of course. Fraction number 2 would be optically inactive because there's no asymmetric carbon. Fraction number 1, optically active. Fraction number 3, optically active. Fraction number 5, I said 5 and wrote 4. Oh my, losing my brain. Fraction number 5, optically active as well. Fraction number 4, optically inactive because it's meso. Fraction number 2 is optically inactive because no asymmetric carbon. Isn't this a fabulous problem that just relates so many of our old things all together? Yeah, it's great. That was so fun. I brought you another one. You should try it. We'll do it together, but you should try it anyway, on your own. Maybe I should get you started before I turn you loose. If we draw it in the same orientation, you can check your answers compared to my answers a little more easily. Here's a butane. If it's a 1-chloro-2-methyl butane, if it's an R 1-chloro-2-methyl-butane, that's got to be dashed, right? 1, 2, 3, 4. Yep, got to be dashed. All right, now it's your turn. Diatomic chlorine in the presence of UV light. Pause, do it. Did you get it all done? Should I talk to you while I'm doing all this? Interesting. All right, if we give them numbers, I did not start at the beginning. I just started giving them numbers. I apologize for the chaos. Give the relationship between all stereoisomers. My numbers 1 and 2 are stereoisomers. Numbers 1 and 2 are diastereomers. My numbers 4 and 5 are enantiomers. And that's all the stereoisomers I've got. Done. If separated by distillation, how many fractions would be obtained? Remember, that's really asking, do you have any pairs of enantiomers? Uh-oh, I do. So I've got 7 molecules, but I would have 6 fractions because 4 and 5 distill as a single fraction. So 6 fractions would be obtained because 4 and 5 distill as a single fraction. Which of these fractions would be optically active and inactive? 4 and 5, definitely inactive. That's a fraction that comes together because it's a pair of enantiomers, it's racemic. Any others that are inactive? Fraction 6 would be inactive because it doesn't have an asymmetric carbon. I drew it like this is an asymmetric carbon. It's not. CH2Cl, CH2Cl, those branches are identical. Fraction number 6, compound number 6, not optically active. But everybody else, 1, 2, 3, and 7, everybody else should be optically active because they don't have any enantiomers. They do have an asymmetric carbon. Yeah. Cool. I like it. You like it? Maybe I like it more. So I've said from the beginning that we could do chlorine or bromine. But so far, every example we've gone through is chlorine instead of bromine. What's the big deal? What's the difference in chlorination versus bromination? If I look at the first step, this is a propagation step. The propagation step is positive 7 kilojoules per mole. Propagation step for chlorine. The propagation step right here for bromine, positive 73 kilojoules per mole. Interesting. The propagation step, the second propagation step for chlorine, my laser's not showing up. Second propagation step for chlorine, negative 108. Second propagation for bromine, negative 109. All right. There's something that's pretty different about those two numbers. What that actually translates to is it tells you that the bromine radical is more selective than the chlorine radical because the bromine radical is less reactive. It can be more choosy about where it reacts. The chlorine radical is very unstable. It plucks hydrogens, abstracts hydrogens lots of places. But the bromine radical is fairly stable, so it can sit around and wait and pluck hydrogen from only the bestest choice. Yep, I said that. Bromine radical, less reactive, therefore more selective. So if I look at these rates, like I saw previously with chlorine, if a primary hydrogen is abstracted at a rate of 1, a secondary hydrogen is abstracted 82 times faster. A tertiary hydrogen is abstracted 1,600 times faster than primary. So what that tells me is the bromine radical is so selective that it preferentially makes the most substituted product only. Chlorine can abstract hydrogens all over the place and replace everything. So we made a lot of products in those practice and more practice examples. If we did the same reactions with chlorine, if we did the same reactions with bromine, we would really only get one isomer in each of those where we abstract only the most substituted hydrogen. Okay, only the hydrogen from the most substituted carbon. Iodine, it's too slow to do this. The iodine radical is so stable itself that it doesn't really abstract hydrogens like this. Fluorine is too exciting, as in it would pluck hydrogens off of a lot of places all the time. Fluorine chemistry, it can get kind of scary. Yeah. Here's what does it all mean? How should I predict products? Chlorination, you should predict both of those products as products. Bromination, you should predict only this product as the product. We're going to talk about the percentages. Hold on. Chlorination would give you substitution at the primary and the tertiary in that example. Bromination should only give you substitution at the tertiary, only at the most stable. Okay, if we look at these percentages, 64 and 36, why is it that way? Well, statistics does play a part. So when we talked about it earlier, we said statistics is not the only thing to consider. Statistics and stability cooperate here. That there are 9 hydrogens that are primary and only 1 hydrogen that's tertiary. So we don't see the statistical ratio of 9 to 1, but we see something that we see that statistics does actually play a little bit of a part. Do I expect you to know these kinds of percentages, 64 and 36? No. It's just statistics plays a part, stability plays a part, intermingled, that's why we get the 64-36. Who cares? We get all tertiary when it's bromine. That's the point of this. So all of that was reactions with alkanes and bromine or chlorine. What if you try to react an alkene with bromine? Well, Alkene with bromine, that's old stuff. We know how that works. It makes that product. Anti-addition, addition reaction, yeah. What if this reaction on the left is not done completely in the dark? What if there's a little bit of light energy around? Uh-oh. Should I do a radical? Should I do an addition? A radical is a substitution. I should have said that. Should I do a radical substitution? Should I do an electrophilic addition? I don't know. It's confusing. I'm not sure what I should do. If I were going to do a radical, where is the most stable radical going to be? Where's the most stable hydrogen going to be abstracted to make the most stable radical? Let me say that one more time. Where's the hydrogen going to be abstracted to make the most stable radical? Should I get radical substitution and electrophilic addition? Oh boy, I don't know. So it's really tough to know if there's light or if this reaction is heated. It's really tough to know whether you should do radical stuff or addition, electrophilic stuff. I don't know. If you want to do radical stuff, a solution for mandatory doing radical stuff is to add something called NBS. This is the structure of NBS, N-bromosuccinimide, NBS and peroxides, because peroxides are radical initiators. They tell you that you're going to do a radical reaction here. So NBS and peroxides, you're going to do radical. What kind of product should you predict if you add NBS and peroxide? Back to, where's the hydrogen that should be abstracted in order to make the most stable radical? All of the carbons in this molecule are secondary. However, this spot right here next door to the alkene is secondary and allylic. This spot is also secondary and allylic. So disregarding stereoisomers, I should make this product because I substitute at the allylic spot. In fact, NBS I will often call a specialty reagent, S-P-E-C-I. Oh boy, S-P-E-C-I-A-L-T-Y. I really can spell, I promise I can. I will call it a specialty reagent that does allylic or benzylic bromination only. If there's not an alkene there, do regular Br2 and light, or Cl2 and light. If there's an alkene, in order to keep from doing potential electrophilic halogenation or radical substitution, in order to prevent confusion, if there's an alkene, you should use NBS so that you can make sure you substitute at the allylic spot only. Whew. What's the product of this thing? I've got an alkene. I'm adding my specialty NBS reagent. I'm going to do allylic bromination. But the problem is I've got not one, not two, but three allylic spots, 3 allylic carbons. All 3 of those positions are considered allylic. Spot number 1 is primary and allylic. Spot number 2 is secondary and allylic. Spot number 3 is tertiary and allylic. So we're trying to make the most stable radical. That means I pluck the tertiary allylic hydrogen. I abstract that one, and that's where my bromine gets added. Fancy. Speaking of addition reactions, this is an old addition reaction. HBr added to an alkene. I'm going to get this product. It's going to go through a carbocation. HBr, the H gets connected to the bottom carbon so that I can make the tertiary carbocation Markovnikov bromide attacks. Done. Well, through old reactions, a chemist, I forget who, discovered if they tried to do that reaction and they had some peroxides in their flask, they did not get that product. They got this product instead, disregarding stereoisomers. They got this product instead. This is the anti-Markovnikov product, and they were shocked, and they didn't understand why at first. So they started investigating. this reaction that we're about to talk about does not work with HCl and peroxides. It only works with HBr and peroxides for the same reason that we've talked about. Bromine radical is more stable, so it's more selective. The same reaction does not work with HCl because the chlorine radical is not stable. Uh-oh, did I give something away? This reaction does not go through a carbocation. This reaction goes through a radical intermediate. But you've told me radicals and carbocations are similar in stability. How the heck does that lead to this product instead of that product? This instead of that. Yeah? Let's draw a mechanism. Oh, joy. All right. Radical mechanisms. They start out with initiation steps. Actually, when I wrote that this time, I'm pretty sure I corrected my spelling last time and still spelled it wrong. Love when that happens. Peroxides are radical initiators. So this mechanism begins with begins with the peroxide falling apart and making a radical. I end up with 2 of those O radicals. Peroxide bonds are not super stable. They go boom sometimes. So this peroxide radical going to continue my reaction and react with HBr, like so, to give me an alcohol that is a very stable compound and a bromine radical. And like we've said previously, the bromine radical is quite stable, so that bromine radical can sit around for a little while until something appealing comes along, and then he starts reacting. He can react in a propagation step, starting with a bromine radical, adding our alkene. Bromine reacts with our alkene like so, in that the bromine makes a new bond down here so that we can make the more stable radical up there in the armpit. Yeah? Isn't it more stable for the radical to be there? Yeah, it is. So then that armpit radical, for lack of a better term, that armpit radical reacts with my HBr, or it could react with, it reacts with my HBr, the end. It reacts with my HBr, like so, to regenerate my bromine radical and create the product that we drew on the previous page as the predicted product. It's the anti-Markovnikov product. Did it go through an unstable intermediate? No, it went through the most stable radical possible. It's just that the order of addition of regular HBr is H gets added first, then Br gets added. In this addition, Br gets added first, then H gets added. In both of those problems, HBr versus HBr with peroxide, you make the most stable intermediate possible. HBr, you make the most stable carbocation possible. HBr and peroxides, you make the most stable radical possible. They're the same but different. Yeah. We've already talked about one way to make a Br go anti-Markovnikov, make an alkyl halide anti-Markovnikov. This is a new way to make an anti-Markovnikov alkyl halide. But this way, one more time, only applies to HBr. It does not apply to HCl. It does not apply to water. Sometimes students want to put water and peroxides and make it go anti-Markovnikov. No, don't do that. It's only HBr and peroxides that can do this because the bromine radical is so stable. All right, that's enough about radicals. We'll talk about polymers next.